Hello friends, in our previous discussion we talked about the principles, operation and characteristics of the operational amplifiers. Op-amps are used in such a wide variety of circuits and applications that it is impossible to cover all of them in one lecture or even in one book. Therefore, we shall be discussing 4 fundamentally important circuits which will give you a foundation in op-amp circuits. Operational amplifiers are often used as comparators to compare the amplitude of one voltage with another. In this application, the op-amp is used in the open loop configuration with the input voltage on one input and a reference voltage on the other. After completing this session, you should be able to describe and analyze the operation of several types of comparator circuits, discuss the operation of a zero level detector, describe the operation of a non-zero level detector, discuss how input noise affects comparator operation, describe the operation of comparators with output bonding, and finally discuss examples of comparator applications. A comparator is a specialized op-amp circuit that compares two input voltages and produces an output that is always at either one of the two states, indicating the greater or less than relationship between the inputs. Comparators provide very fast switching times and may have additional capabilities such as fast propagation delay or internal reference voltages to optimize the comparison function. For example, some ultra high speed comparators can have propagation delays of as little as 500 picoseconds. Because the output is always in one of the two states, comparators are often used to interface between an analog and digital circuit. For less critical applications, an op-amp running without negative feedback is often used as a comparator. Although op-amps are much slower and lack other special features, they have very high open loop gain, which enables them to detect very tiny differences in the inputs. In general, comparators cannot be used as op-amps, but op-amps can be used as comparators in non-critical applications. Because an op-amp without negative feedback is essentially a comparator, we will look at the comparison function using a typical op-amp. Zero level detection. One application of an op-amp used as a comparator is to determine when an input voltage exceeds a certain level. Figure here shows a zero level detector. Notice that the inverting input is grounded to produce a zero level and that the input signal voltage is applied to the non-inverting input. Because of the high open loop voltage gain, a very small difference voltage between the two inputs drives the amplifier into saturation, causing the output voltage to go to its limit. For example, consider an op-amp having AOL equal to 100,000. A voltage difference of only 0.25 millivolt between the inputs could produce an output voltage of 25 volt if the op-amp were capable. However, since most op-amps have maximum output voltage limitations near the value of their DC supply voltages, the device would be driven into saturation. Figure here shows the result of a sinusoidal input voltage applied to the non-inverting input of the zero level detector. When the sine wave is positive, the output is at its maximum positive level. When the sine wave crosses 0, the amplifier is driven to its opposite state and the output goes to its maximum negative level as shown. As you can see, the zero level detector can be used as a squaring circuit to produce a square wave from a sine wave. Non-zero level detection. The zero level detector shown earlier can be modified to detect positive and negative voltages by connecting a fixed reference voltage source to the inverting input as shown in figure. A more practical arrangement is shown in this figure using a voltage divider to set the reference voltage V reference as follows, where V reference is equal to R2 over R1 plus R2 into positive V. Here positive V is the positive op amp DC supply voltage. Another circuit shown here uses a Zener diode to set the reference voltage. As long as V in is less than V reference, the output remains at the maximum negative level. When the input voltage exceeds the reference voltage, the output goes to its maximum positive voltage as shown in this figure with the sinusoidal input voltage. Effects of input noise on comparator operation. In many practical situations, noise or unwanted voltage fluctuations appears on the input line. This noise voltage becomes superimposed on the input voltage as shown in figure for the case of a sine wave and can cause a comparator to erratically switch output states. In order to understand the potential effects of noise voltage, consider a low frequency sinusoidal voltage applied to the non-inverting input of an op amp comparator used as a zero level detector as shown in figure. Then this figure here shows the input sine wave plus noise and the resulting output. When the sine wave approaches 0, the fluctuations due to noise may cause the total input to vary above and below 0 several times, thus producing an erratic output voltage. Reducing noise effects with hysteresis. An erratic output voltage caused by noise on the input occurs because the op amp comparator switches from its negative output state to its positive output state at the same input voltage level that causes it to switch in the opposite direction from positive to negative. This unstable condition occurs when the input voltage hovers around the reference voltage and any small noise fluctuations cause the comparator to switch first one way and then the other. In order to make the comparator less sensitive to noise, a technique incorporating positive feedback called hysteresis can be used. Basically, hysteresis means that there is a higher reference level when the input voltage goes from a lower to higher value than when it goes from a higher to lower value. A good example of hysteresis is a common household thermostat that turns the furnace on at one temperature and off at another. The two reference levels are referred to as upper trigger point and the lower trigger point. This two level hysteresis is established with a positive feedback arrangement as shown in figure here. Notice that the non-inverting input is connected to a resistive voltage divider such that a portion of the output voltage is fed back to the input. The input signal is applied to the inverting input in this case. The basic operation of the comparator with hysteresis is illustrated in this figure. Assume that the output voltage is at its positive maximum, that is plus V out maximum. The voltage fed back to the non-inverting input is V UTP and is expressed as V UTP is equal to R2 over R1 plus R2 into positive V out maximum. When V in exceeds V UTP, the output voltage drops to its negative maximum. Now the voltage fed back to the non-inverting input is VLTP and is expressed as VLTP is equal to R2 over R1 plus R2 into negative V out maximum. The input voltage must now fall below VLTP as shown here before the device will switch from the maximum negative voltage back to the maximum positive voltage. This means that a small amount of noise voltage has no effect on the output as illustrated by this figure. A comparator with built-in hysteresis is sometimes known as a Schmitt trigger. The amount of hysteresis is defined by the difference of the two trigger levels. Output bounding. In some applications, it is necessary to limit the output voltage levels of a comparator to a value less than that provided by the saturated op amp. A single Zener diode can be used as shown in figure to limit the output voltage to the Zener voltage in one direction and to the forward diode voltage drop in the other. This process of limiting the output range is called bounding. Since the anode of the Zener is connected to the inverting input, it is at virtual ground. Therefore, when the output voltage reaches a positive value equal to the Zener voltage, it limits at that value as illustrated in this figure. When the output switches negative, the Zener acts as a regular diode and becomes forward biased at 0.7 volt, limiting the negative output voltage to this value as shown here. Turning the Zener around limits the output voltage in the opposite direction. Two Zener diodes arranged as shown in this figure limit the output voltage to the Zener voltage plus the forward voltage drop of the forward biased Zener, both positively and negatively. Comparator applications. Over temperature sensing circuit. Figure here shows an op amp comparator used in a precision over temperature sensing circuit to determine when the temperature reaches a certain critical value. The circuit consists of a Wheatstone bridge with the op amp used to detect when the bridge is balanced. One leg of the bridge contains a thermistor R1, which is a temperature sensing resistor with a negative temperature coefficient, that is, its resistance decreases as temperature increases. The potentiometer R2 is set at a value equal to the resistance of the thermistor at the critical temperature. At normal temperatures, that is below critical, R1 is greater than R2, thus creating an unbalanced condition that drives the op amp to its low saturated output level and keeps transistor Q1 off. As the temperature increases, the resistance of the thermistor decreases. When the temperature reaches the critical value, R1 becomes equal to R2 and the bridge becomes balanced, since R3 is equal to R4. At this point, the op amp switches to its high saturated output value, turning Q1 on. This energizes the relay, which can be used to activate an alarm or initiate an appropriate response to the over temperature condition. Analog to digital conversion. A to D conversion is a common interfacing process often used when a linear analog system must provide inputs to digital system. Many methods for A to D conversion are available. However, in this discussion, only one type is used to demonstrate the concept. The simultaneous or flash method of A to D conversion uses parallel comparators to compare the linear input signal with various reference voltages developed by a voltage divider. When the input voltage exceeds the reference voltage for a given comparator, a high level is produced on that comparator's output. Figure here shows an analog to digital converter that produces 3 digital binary numbers on its output, which represents the values of the analog input voltage as it changes. This converter requires 7 comparators. In general, 2 to the power n minus 1 comparators are required for conversion to an n digit binary number. The large number of comparators necessary for a reasonably sized binary number is one of the drawbacks of the simultaneous ADC, but IC technology has reduced the problem somewhat by combining multiple comparators and associated circuits on a single IC chip. For example, 6 or 8-bit flash converters are readily available. These ADCs are useful in applications that require the fastest possible conversion times, such as video processing. In figure shown, the reference voltage for each comparator is set by the resistive voltage divider circuit and V reference. The output of each comparator is connected to an input of the priority encoder. The priority encoder is a digital device that produces a binary number on its output representing the highest value input. The encoder samples its input when a pulse occurs on the enable line and a 3-digit binary number proportional to the value of the analog input signal appears on the encoder's output. The sampling rate determines the accuracy with which the sequence of binary numbers represents the changing input signal. The more samples taken in a given unit of time, the more accurately the analog signal is represented in digital form. So, here we come to the end of this lecture and therefore, we sum up. In this lecture, we learned that in an op-amp comparator, when the input voltage exceeds a specified reference voltage, the output changes state. Hysteresis gives an op-amp noise immunity. A comparator switches to one state when the input reaches the upper trigger point and back to the other state when the input drops below the lower trigger point. The difference between UTP and LTP is the hysteresis voltage. Bounding limits the output amplitude of a comparator. So friends, this is it for today. See you in the next lecture. Thank you very much.